Thank you for that. I don't have to introduce myself anymore. That's very convenient. But I am Martin. I am part of the product management team at Plexxi. Been there for 7, 8, 9 months, something along those lines. Some of you may have heard my voice explaining some of this on Ethan and Greg's podcast a couple of months ago. I'm hoping to, speak a little slower this time. I have a few slides. I don't have too many, so there's still some bacon left to give to hungry kids. But I figured I use a couple of slides just as pictures to save myself from doing too much drawing, but I am going to go to the whiteboard. What I'm going to try and do is explain, in the next 45 minutes or so, explain some of the basic concepts behind Plexxi. Matt's already mentioned affinities. Go a little bit through what is this thing called an affinity. And then I'm going to explain the network portion of a Plexxi solution, and I'm going to deliberately skip a little bit about how you actually define an affinity and how we actually control the network, define topologies and those sort of things. I'll let that to Simon. Simon's actually going to walk through, hopefully mostly a whiteboard session with perhaps a little bit of demo. But I want to make sure that you have a fundamental understanding of what is that physical thing that we build, right? These affinities on top of. We've tried these discussions the other way around as well, and especially for those that are very well versed in networking, it's always good to give sort of the networking view first and then layer the other stuff on top. So that's what I'm going to try and do. My handy dandy remote. So to give you an example of this concept of affinities, what are affinities? Microsoft did a study a couple of years ago, 3 years ago, actually probably not 4 years ago, and they measured communications between 1,500 servers in one of their data centers. So they essentially instrumented 1,500 servers, and they measured all the communications between them. And the servers were essentially numbered from top left is number 1 all the way to 1,500 at the end. And they collected a whole ton of data. I mean, the paper that's mentioned below, you can find it on the internet. It's got a whole bunch of data associated with that, but one that we picked out was this scatter plot that they created. And this scatter plot represents what they believe was about a 10-second representative sample of communications between servers. And the darkness of the red give an indication of how much communication was happening between servers in that 10-second sample that they picked. And there's a lot of interesting things you can see in this, right? There's obviously, the first thing that you very obviously see is this diagonal pattern. Now, in the paper it's explained, right? This was a very well engineered data center, right? Applications were carefully placed together if they had some sort of relationship. If they was expected to have a lot of network communication between them, they would place them within a rack or right next to each other. So there was quite a bit of thought that had gone in. Where do we place the applications within this 1,500 server data center? And what you see, the diagonal line, if you sort of look at what that means, from and to, that means that servers that were numbered close together had a lot of communications together. Fairly obvious, right? If you place applications that have a network relationship with each other in the same rack, they're gonna communicate like that, and it's gonna show up like that. So that's sort of the obvious pattern. This is sort of that was the exact point of their engineering. Let's make sure that those that communicate often are nice and close together. But there was a whole bunch of other patterns that you can see in there. You can see here the horizontal lines and the vertical lines. And the horizontal lines essentially said, right, there's certain servers that everybody talks to. Right? If you take one of this one, or one up here, or one in the middle, all these servers want to talk to that one specific destination server. Similarly, in the other way around, for a vertical, right, there are certain servers that speak to almost everybody else. So there's patterns here. Now, the biggest pattern that is perhaps not obvious until you do this is how few servers actually communicate with each other. Right? The vast majority of this is, right, if you turn this way, is red. And red means here, they do not communicate at all. Right? So you've built this entire infrastructure for very sparse communications between servers in a fairly well-engineered network. Now, obviously things change, right? This is about 3.5 years ago. This was not a virtualized environment, right? So these were specific servers with specific applications. But it very clearly shows that there's applications that have relationships with each other, right? There's obvious communications patterns here between applications that live in certain places. And those applications, while we may virtualize them and we may break them apart a little bit, these relationships still exist. What's going to make it harder is, in this case, you can actually, Microsoft knowing their applications fairly well, they can be fairly clever in their engineering of where do I place these applications to make sure that I get the best connectivity or the best needed connectivity for those applications by placing them near each other. In a virtualized environment, now, I don't actually believe that anybody's going to build a virtual environment where any application can just randomly go everywhere. But the amount of control, the amount of distribution of applications or pieces of applications is likely going to be slightly more distributed than in a network that is one server, one application, very carefully engineered. These relationships between applications don't change. However, these applications now start to move a little bit, right? Again, I'm not a believer that this is going to randomly move from anywhere, but you are going to see, especially these pockets here, they're going to get a little wider, right? You're going to define a set of racks or a cluster of servers that run an application or a set of applications. It may not be an entire data center, but they're going to be a bunch of them that are somewhere near each other. So these relationships exist. Now, if you then take that, if you make the assumption that these relationships are going to exist, they exist now, they existed then, they will exist now, you can actually point out where these relationships are. Right? I mean, the obvious ones obviously are the diagonal ones, but there's a whole bunch of little bubbles. I just drew a circle around some of them that are very obvious relationships between applications, communications relationship between applications. That's the basic concept behind what we call an affinity. An affinity is a set of applications that have a communication relationship between each other. And as you can see, it is not everybody to everybody. This is not I'm going to build a 1,500, 2,000, 3,000 endpoint data center, and I am going to expect everybody's going to talk to everybody. They may at some point for a very little bit of data, but ultimately the most volume of the data is going to be articulated between certain sets of applications. That's what I have no idea why it does that. That's what affinities are, relationship between applications. Now, once you have relationships between applications, and once you have some sense of trying to articulate what they are, maybe you want to describe what they need. Right? Instead of just saying, okay, I know there's applications that need to communicate, perhaps you can quantify a little bit of what type of communication these applications are expecting. Right? Are they expecting lots of bandwidth? Are they expecting low latency? Are they expecting to be separated from everybody else? Are they expected to get preferential treatment over someone else? Right? There's a whole bunch of things that sort of naturally we can come up with of describing what applications would like to have in their communications. That is the concept behind affinities. The ability to articulate what applications need, right? Which applications need to communicate, not exclusively, but which are the ones that we care the most about, and some set of attributes that describe what kind of communications do we want those applications to have. That's what affinities are. Let me pause for a second. Is that a clear enough explanation of affinities? Yeah. Good. Now, so Plexxi took that notion of affinities and they're like, okay, so if we understand and we believe that there is a relationship between applications and how they communicate, and we want to describe how they want to communicate, we should be able to actually create a network infrastructure that provides that to those applications, right? That is the notion of what affinity networking solves, right? We take the start of, let's ask the applications, right? And some applications can articulate them by themselves. Some we need to do it, the operators need to do it as a proxy of describing what these applications need. But let's take those applications that are really important, not every single one of them, the ones that are really important, and describe what kind of communication they need between what members of that cluster or set of applications. Once we know that, can we build a topology? Can we build a network topology that matches what we need? And we're not just talking about can we forward packets the right way. That's where we started, but like Matt said, can we actually build a physical topology that best matches what we've just described as what the applications really need? And once we've built that, can we then take the knowledge of these affinities and layer the traffic on top of that topology, that physical and logical topology that we've just created? That's what we do. We define affinities, we create a physical network topology, and then we layer the traffic on top of that to best match the description or the attributes that have been described for those affinities that have been articulated.
And then when we need to, we can change it.
Yes. I mean, the beauty of all of this is not a one-time shot. Right? If this is a one-time shot, you can do this as a pre-sales or pre-installation network engineering event. Right? You can go figure out what you want, design it, implement it, wire it, and be done with it. Things change. Applications change. Applications upgrade. They get bigger. They get smaller. They disappear. Their communication changes. Right? So these relationships between applications changes. They don't necessarily change on a minute-by-minute basis, but over time they will change. And what we want to make sure we can provide is a mechanism that you can actually change the network along the way with the changing need of these applications. Whether that's traffic related, whether that's application related, whether that's changing requirements. Right? We want to be able to take that information, recalculate topology, both physical and logical topology, and reapply that to the network. It's dynamic. I'm almost at the end of my slides, Ethan, so make sure we get some bacon left.
Very good.
All right, so I wanted to get this. I wanted to put this picture in there because I cannot draw this on the whiteboard. I could, but it wouldn't look anywhere near as pretty as this. This is our switch, right? As Matt explained, we believe we need a mechanism to implement that dynamic topology, physical and logical topology. Whenever we take, if we were to take, and this is, this was part of, before my time, but part of the initial thought process in Plexxi is, can we apply this to pick your random switch? And pieces of it, probably, because you'll find, I'll explain in a minute here, we're using standard commercial silicon in here, so there's other switches that have that as well. But there is this part of physical topology, right? Can we change the connectivity of how this switch connects to other switches? Can we change that on the fly? Can we change that based on what the affinities are looking for, based on what we've described as what the network needs? Such a switch doesn't exist, which was sort of the trigger for us to say, we need to build our own hardware to allow us to physically change the network connectivity between all the switches. So let me just walk through it. Right from the front, it looks fairly common. It's a 10 gig E ports, 32 10 gig E's. You'll see there's 1, 2, 3, 4 QSFPs on here. Plain Ethernet, 40 gig E, 10 gig E. What you would see from everyone else. Various console connectors, everything else. I don't show the back here, but the back's got fans. It's got power supplies. It's got. You take yourself a standard 1U top of rack switch, and the front's going to look pretty similar to this, except for this connector here on the left. Right? The connector on the left is our mechanism of interconnecting switches together. Right? It's an NTP connector, which is a standard connector. It's got 12 fibers coming out of each port, six in and 6 out. And that's how we create a topology between our switches. And I have a picture a little bit later, and then I have the whiteboard to go and explain that. But if you open up the switch, you'll see that it's a little bit different, right? You may notice that this is actually fairly deep, right, for a standard 1U top of rack switch. If you look at the components inside it, obviously we've got the front ports with the transceivers and all that stuff. We have a CPU complex. We're actually using a multi-core i5 with 8 gig of memory, so it's got a pretty beefy and powerful CPU complex in there. Commercial switching ASIC. Again, no secret, we're using Broadcom switching ASIC in here. We're using Trident Plus today, Trident 2. Give it a month or so, and then you open up everybody else's top of rack, 10 gig top of rack switch, and this is going to look pretty much the same. This part is almost going to be the same. It's at the end where things are a little bit different. And the first thing you notice is this and a whole bunch of wires. With the premise that we want to change the physical topology of how switches are connected. Right? The only real way to do that is one, wireless. Not necessarily a good option just yet. Give it a couple of years and maybe it will be. The other one is optical multiplexing. So we're actually using optical multiplexing, WDM, inside the switch to connect two other switches. So this whole complex in here that you see with, a whole bunch of wires, these are a whole bunch, in this case 24 optical transceivers that go to a little bit of Plexxi optical magic, let's call it that. But essentially, right, this is a combination of some muxing, some demuxing, some cross-connect, right, some optical pieces in here that allow us to take 24 10 gig channels out of our switching ASIC, mux them together, and then bring them out these front panel ports. That's ultimately what we do. And these front panel ports, you'll see in a minute, we actually connect these switches together in a ring topology. It's one go to the left, the physical, one cable goes to the switch on the left, one cable goes to the switch on the right, and we create a ring topology with that. But on top of these connectors here, there's 24 10 gig channels that are running over that ring interconnect to the switches near us.
So is that 12 by 10 east, 12 by 10 west?
Yes. So there is, I'll explain that in a minute. So there is we've picked a default topology of where those 24 10 gig wavelengths sort of end up going. We actually have the ability to change that. So you can actually redirect waves from one place to the other. But your basic premise is correct. There's 12 going one way and 12 going the other way. Beyond that, right, power supplies, obviously two power supplies, they're like 650 or 660 watts. The switch will only consume, similar to what another top of rack switch will consume, 200, 250 watts or something like that. But that's the physical switch, right? And the key in here is, yes, it looks like a top of rack switch, right? But the main thing that's different in here is that we needed a mechanism to change how switches are connected together. Right? If we believe that our affinities tell us that we need more bandwidth to one side of the network than the other side of the network, we want the ability to move that bandwidth, and not just by allocated QoS and everything else. We actually want to physically move bandwidth from one side of the ring to another side of the ring, or between one switch to another switch. And that's what the optical technology allows us to do. I'll get to how that topology looks in a second. Any questions on the physical switch? Yes?
So is it a ROADM, essentially? I mean, it sounds like you can reconfigure the channels.
So we can reconfigure the channels, but not in a ROADM way. It's more of think about it as a cross-connect. So there is basic muxing and demuxing. Then we get into a cross-connect, and within the cross-connect, we can redirect waves back out to somewhere else.
So timing switching. Okay.
Now, someone that's thought a little further here might say, well, if you got 24 channels, 24 waves, this is CWDM in this specific instance, 24 channels, we reuse a few because there's not that many in CWDM, do I really need 12 fibers or 6 fibers in each direction to go and do that? Let me explain that in a minute as well. There's a reason why we've got a few more fibers than you would possibly need. You could probably get away with 4 fibers for 24 channels, but I'll explain to you why we have that. So my last slide, so that the hungry kids can eat some bacon. I'll stop using that now. I think I've overused it already. So, as I mentioned, right? So physically, our switches are connected in a ring topology, right? So switch 1 is connected to switch 2 on one side, and switch 10, 12, whatever it is on the other side, and we physically create a ring. Now, that's just a physical wiring, right? So there's physical wiring from each switch through these NTP cables to my switch on the left and my switch on the right. let me get to physical topology first, and then I'll explain the control of
And also, as you can see, first mentioned, there's some software on the right.
Yeah, there's
But
some,
after mine's finished, I'm going to talk a lot about the software, because the software is the key element to how we control this. But we wanted to lay the foundation for the hardware first.
not working too well either.
You better mark it.
We'll get there. So if you take a ring topology, I need to draw a few more here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's show some more. 10, 11, something like this. All right, so physically these switches are connected just like up there. But that's just a physical. Those are just where the wires happen to go. We haven't actually talked about how those 24 10 gig wavelengths, how those sort of end up, where they end up. So we have, we call it a base topology. It is when you take the box, you take it out, you power it on, you connect it to the switches next to you. What happens? Where do those 24 waves end up? And let me do it in a different color. Assuming that I can find one that works. So if I take this switch as an example, if the switch just starts up without doing anything else, these are the waves that I'm drawing here. These are all 10 gig waves. 1, 2, 3, 4. Let me add one more switch in here. Just to make it complete. So those waves are actually configured in such a way that this switch has 4 10 gig waves, so 40 gig connectivity to the switches right next to it. It then has 2 10 gig connectivity to the switches 1 step away. Same with 2 step away, 3 and 4 in one direction, and very similar in the other direction. 40 gig to my neighbor immediately on the left, 20 gig to the one beyond that, 20, 20, and 20. That's how those 24 waves are initially deployed. Now, obviously, because there's only a cable that goes from here to here to here to here, right? These 2 waves here pass through this cable to this cable to this cable, and then here ultimately they terminate into what's called the Broadcom. In the Broadcom, that's where they end up being a physical, Ethernet connection, a point-to-point connection between this switch, and that switch over there.
They pass through those switches optically, not through switch hops.
Yeah, so this connectivity here, this optical connectivity that passes through here is completely passive. And this is the reason why we need those extra fibers. Right? We want to make sure that we can actually take these waves and pass it through 4 switches on either side of us without that switch needing any configuration, any power, any active components. So that's why we layer these waves on top of a few more fibers than we would actually need, but allows us to take certain one of these fibers and simply passively pass them through from switch to switch to switch without needing a single electrical component in between. So in this case, I can actually power down this switch and this switch. This connectivity will remain. As long as these cables are plugged in, that connectivity will remain because it passively passes through.
Is there a reason you didn't use dense wave?
Awesome. Yeah, I mean, dense wave optics are probably, the ones that we would have to use internally are probably somewhere between $800 and $1,000 each. 24 of those, right, starts that up. Now again, right, so today we use CWDM, and because it was the most effective way for us to go and do that. We're not necessarily married to CWDM or anything like that. It was just a very convenient and cost-effective way for us to achieve what we want, right? What we wanted is we want connectivity between switches that we can change, right? Because while this may be our default topology, right? Switch comes up, this is how they will be connected. I can actually, because of the optical components in here, I can actually take, because obviously this guy has the same thing, right? He's got 1, 2, 3, 4 here, 1, 2, 3, 4, and he's got that, 2 there, 2 there, right? He's got all that as well, so you create this entire mesh. I can actually take, if I need more connectivity between these two switches, so like, oh, I got 20, my affinities really could use 30 or 40 gig of direct connectivity between this switch and that switch over there. I can actually steal it. I can actually take these two, optically connect them through. So it looks like these guys are actually directly connected, right? Simply by configuring the optics in here to redirect that. Without a switch hop, I'm going optically all the way through from this switch to this switch. I now all of a sudden have 40 gig between these two switches.
So you had mentioned you could pull 2 of those guys out as long as that you were still through as passive, all that good stuff, but because you were effectively hypercubed, logically,
Yes, in a sense.
you can pull those 2 totally out of the mix, and because I have a path back to other people, I still have a...
Correct.
I have the other half of the circle, so...
Correct, right? I mean, so from a ring perspective, right? And I was hoping someone was going to ask a 1990s token ring kind of question, but you didn't, which is good. So
I got one.
There was a price.
Do you support 16,000 byte MTUs?
16 byte MT 16.
16,000. You can do 16,000 byte token. Am I the only person that remembers that?
Yes.
Oh, okay.
No, I remember you do 64,000.
I know it was half prompted, but you get the token for that.
Wow.
So physically it's a ring, right? But there's no tokens, right? There's no concept of that. This is just a pure mechanism of convenient connectivity for an ever-expanding thing. What you see is the red lines here actually indicate the real connectivity between the switches, which are
Physically,
point to
it's a ring.
point to point.
Logically, it's point to point.
Absolutely correct.
You can create an overlay. You can say, this switch has 12 connections that you can then terminate anywhere.
Correct.
So if you want a 10 gig here, you've got a loop going 2 ways, 110, 110, terminate it.
Correct.
If you want 40, then take 2 20s.
Correct.
And then 40.
Correct.
But you've got finite number of IOs on the fabric in the core.
Absolutely, right? I mean, so every switch here, I mean, obviously, right, the way we've divided it, every switch here has 24 waves that leave the box, right? That we've designated as, in someone else's solution, that's okay, I'm not, in someone else's solution, it may be an uplink port, right? Or if it's a spine and leaf, right, those are your uplinks to your spine. Right? We've designated 24 ports out of the 64 in the current case. Out of the 64, we've designated those to, let's call them fabric connections, uplink connections, whatever they may be. And right, those we've layered or connected to other switches within that ring.
So I get the architecture, and that's great. How does this scale? How does this scale beyond what you've drawn up there?
So
because you have physical and passive path. So how do you scale that?
So today, right? So the connectivity that we do, so the optics that we have, and the way we've got them layered, right? The connectivity with the loss budgets and everything else. The connectivity that we have is five switches to our left and 5 switches to our right. That's how far we can go without exceeding our loss budget, our optical loss budget, right?
But hold on. That's not the end.
But you can make this ring as large as you want it to make. I drew 11 here, which creates a full mesh of connectivity between all the switches. I can create a ring of 20 switches. I won't have a full mesh. Every switch will see the 5 switches nearest to it, so you get lots of partial meshes that have the connectivity. And for me, from switch 1, right, if I got 20 switches in the network, for me, switch 1 to get to switch 10, I obviously do not have direct connectivity, right? So my path is going to go from switch 1 to switch 5 to switch 10. That's how I get there. Now, at some point, does that diameter turn into, okay, how many hops do I have to get through to get from one place to the other? No, there is, and it's going to be different for every customer. There's no logical, we put a heart limit of 250 in there just because it's sounded like a good number.
Software guy saying, how much do you want us to test? We have to give them
so that there's no real physical limitation. There becomes a deployment or an architectural solution, limitation to say like, okay, if I need to get from the extreme left of my network to the extreme right of my network, how many hops can I endure? Now, remember, with the affinities, we can actually start stitching these things together optically, right? So if I have a ring of 20 of these, and I have an affinity that tells me that there's a set of applications here and a set of applications there that have a high bandwidth or a low latency need to communicate, I can actually optically string these together so that it looks like they have a direct path between them.
And you can do that 25, you can do that how far deep though, optically?
There's no limit because it gets regenerated.
Okay, because you're effectively dedicating your true physical path to do that.
Correct.
Okay.
Yeah. And the way to think, if you think about this as a linear line, right, every switch has essentially like a wingspan of 5 and 5, and that kind of creates this overlapping thing. And you know, so there are cases where you may want to you know, go beyond it, but there is still some locality and benefit to locality, right? What we want to be able to do is also accommodate you know, other cases, maybe that's a demotion or.
Well, it goes back to your original thing from Microsoft, that they were very intelligent about how they laid the things out. What they couldn't do is they couldn't affect the architecture. So you're smart about how you lay it out, and then you use your architecture to draw a straight line.
So
Again.
you're absolutely correct.
I
Right?
just-
And there is a premise in our solution, right? That there is locality in communications within a data center.
I'm good.
Right? And locality, in Microsoft's terms, right, that locality was enforced by hand, right? They actually put applications near each other. In a virtualized environment, that will get a little bit more gray, but you guys tell me if I'm wrong. I'm not a believer that people will build a uniform data center of thousands of servers and applications just go willy-nilly wherever the heck they need to go. Right? People will designate areas of applications right, where they have perhaps some freedom within a set of racks or within a set of servers that people can move into their backups. But I'm not expecting people to just go randomly assign applications to wherever the heck they wanted to put within a data center and therefore have random communication needs.
I kind of agree with you. I would like that to happen. I am learning that that is not happening. That server people just are all over the place and don't seem to be able to plan. Because one of the things I'd like for troubleshooting is some localization, as in vMotion occurs between this set of racks, and maybe it's some here and some there, but if I have a physical layer problem, I want to correlate that with my application problem. But what I'm consistently hearing is, ain't gonna happen, dude. So, not to challenge you.
No, I'm with you. To me, it's like, so it's almost like, so the network is one part of driving that, right? Because regardless of how good any of our solutions are going to be, local switching is always going to be cheaper, better, higher performance than remote switching, right? Regardless of whether it's our solution or someone else's, right? There is a cost of going further away. Storage, in my mind, storage will actually be the one that drives locality more than anything else.
Well, what I'm seeing is it's a function of how data centers get built out. Nobody wants to incur the cost of building a set of empty racks until they absolutely have to. And so what happens is you have space wars, and you can't put new servers, new hypervisor hosts into existing racks to preserve locality. And then you get this new row built out, and everybody and their cousin needs to expand their services into that new.
Well, so just a quick point too, you know, what we're talking about here is also the simplest implementation of this, right? So what we actually see our customers doing is, you know, sometimes they need a really sparse thing, like in a cloud environment where tenants are generally, you know, not going to communicate with other tenants across the data center, right? So they can build it very sparse. In a more classic enterprise data center, they may build smaller rings and connect them together. Today we do that by connecting electrically, but in our roadmap we actually have a product coming out where we can actually create what we call a two-dimensional or a four-dimensional ring essentially. So instead of just being able to go east-west, now I can optically connect across my rings.
And that probably answers my other question,
That's
which
cool.
is every time you stitch, you're using up scarce resources.
Correct.
So I'm
Correct.
understanding that. It's like using, in DWDM, you're using up lambdas.
So you're absolutely correct, right? And you know, that's why there's, in terms of scaling, right? I mean, there's logical scaling of how big would you grow one ring, right, before you run out of, you know, those type of resources. Right? We're not putting a limit on it, but there's going to be a practical deployment limit, which is going to be different, right, depending on how well engineered the data center is. For us to grow to hyperscale, is not so much to grow a ring and just, you know, keep growing and growing and growing. We are actually going to add dimensions, right? So instead of having one ring, you know, our goal is to get, and this is actually not that far away, our goal is to do this. Right? Is to actually create Manhattan-style grids of rings interconnected that way, with full connectivity optically and electrically right, across all of those.
The key thing is once we have the computational power to compute paths, which is where when we talk about the software, because really what this boils down to is a math problem, right? If I have all these different ways to get from here to here, and my goal is to leverage the advantage of the optical stuff and apply that to workloads that care about it, whether it's for low hop count or for high bandwidth, I can figure all that out in software. So once I've solved that problem, I can apply lots of different ways to actually make that, give me more computing freedom to solve that problem. So before we go on to the forwarding architecture, it just leads us to say, look, the net of this is what we've done is said leaf-spine didn't work for what we were trying to do because it basically has a fixed wiring pattern, right? And I kind of said we want to free the wires. And if you look at kind of leaf-spine, you say, okay, I have to kind of decide my oversubscription from day one when I cable the network. What we wanted to do is have a variable oversubscription. We wanted to say, okay, this part of the network needs really low oversubscription. This part may need really high oversubscription. You can't easily do that when you statically kind of allocate capacity based on a wiring pattern. So what we've tried to do is replace the spine layer with a more flexible optical layer, and that's kind of what you see here.
So I've got a couple of questions. So with 10 gig ports on each of the switches, I'm assuming in most data centers, or at least a lot of them, you're going to be having a top of row switch sitting below that, linking up to it, unless you have all your servers on 10 gig, right? Is there support for Ethernet aggregation or MLAG or something along those lines for your uplinks?
So there is, right? So there is a we can actually do a few things here. We can do multi-homing like this, either from a single switch or from a single server, right? Servers that are multi-homed. Right, and in the case of a server, this will appear as a lag group. Of course, for us, it's MLAG-ish. It's not MLAG because we got our own way of dealing, with preventing loops and all those sort of things, which is what that is. But ultimately, what this does is it'll accept traffic on either one of these links, and then we will load balance the destination MAC addresses between the two links on the way back.
Okay. And we've talked about switching, which layer 2. How about layer 3? Is there
so let me explain layer 2 forwarding on top of this, right? Because I've only talked about physical so far. I haven't even talked about how we actually forward traffic. So let me explain how we actually build forwarding topologies on top of that, and then get to layer 3 how that works.
Can I squeeze in one layer 1 question real quick before we get out of that? What's the latency implication of not doing an OEO in between on your transit L2 or actually your transit physical nodes? What's latency? Is there any reduction there by that?
So a regular switch hop, right, which is the same as everybody using this chipset, right? It's 600, 700, 800 nanoseconds on the current version of Trident, and it'll drop to 400 or 500 or so in the next version, right, which is standard Broadcom latency. Right, so if you were actually do switch hops, right, and I'll get to the forwarding architecture, if you would do switch hops from here to here, you would incur that latency every time you go through that. Optically, right, we're talking, and it doesn't really matter how many switches you go through, we're talking in the order of 20 to 30 nanoseconds, right, to get from one place to the other. There's a little bit of delay. There's no delay in the transceiver. There's really no delay in terms of distance, unless you run these really far. The transceivers we have in here can actually run 10 kilometers, so you can pull them apart quite a bit, but the distance is not really there. It's the actual muxing and demuxing that's consuming most of the delay here.
So you're not photonic end to end. So your lambda's terminating on each box as you go.
No. It is truly passive.
Okay, so you're
all the way through here.
Yeah. Okay. Great. You're optical all the way through.
They're right. So this is what I meant, right? You can actually power these guys off.
Yeah.
Right. It is purely passive.
Only other thing is, so I assume you can drain traffic. So when you need to add a node into the ring, and then when you're adding second rings, that sounded like you said that would be electric, and then in the future theoretically there'd be a 4-way.
2 degrees, right?
Okay.
So we have 40 gig ports. We stack them like kind of stack donuts. And the product that's going to come out later this year is going to have an extra 2 degrees, so you can actually cable. We don't like to say north-south because we're trying to think flat, but it's 2 pairs of east and 2 pairs of west.
Yeah, so east 1 and east 2. Yeah.
I'm going to throw one more. I'm going to throw one more base layer question on real quick. This is technology that at best has been boiled down to a metro play before. You guys have brought it to the data center.
Correct.
Because it's played metro and carrier in the past, with the right optics, could you effectively extend this between long-haul data centers and do a full mesh over long-haul data centers?
So it's probably a topic we can talk about for another hour or two.
Yes or no is cool.
So the answer is absolutely yes, right? With the optics that are currently built into this, right? We can push this about 10 kilometers. Depends a little bit on the loss budget and what sits in between. There is other solutions. Be happy to draw those on a whiteboard with you. There's other solutions where we can actually bring this and bring specific lambdas into either CWDM into true optical carrier equipment, transform it to VWDM, whatever it may be, and actually transport this well across.
Cool.
Right? Even though this cable, right, the cable that we have here, it may look unusual, but it's standard MPP cable. We can actually break it out, right? We can actually take one of these, break it out into 12 individual SC connectors to a patch panel, and we can take each one of these to wherever we want to be. Right? There's how we layer the waves on top of these fibers is very well defined, so we can actually pick and choose. If you need to take a specific portion of these and want to bring them out to long distance optical gear, you can absolutely do that. Excellent. Sir, in the back.
Hi, Martin. I got a question for you. Two things. What if one of those switches loses power? What happens?
So if
Which
they're
one?
connected in a ring.
Pick one. Like
Pick
the
one.
switch.
So this one, right? This one loses power right here.
Yeah,
So
there you go.
the only thing that you will lose is all traffic that goes to or through this switch, electrically to or through this switch, right? Optical, this never sees a difference, this never sees a difference, right? So the connectivity, optical connectivity through here, not impacted whatsoever. It's only traffic that terminates on here or is otherwise, and I need to get to my forwarding calls for that, is otherwise part of electrical or
So the
switching
opticals
forwarding.
pass through.
Opticals
so the
pass
opticals
through.
pass through, lose a switch, the ring's not broken.
Correct.
It's not
Correct.
broken.
These guys will these guys, all the switches talk to each other, right? They
Yeah.
realize who's on the ring, they realize who their neighbors is. This guy will realize his neighbor is gone. We'll see that his new neighbor is this guy, and they just keep going as if nothing's happened.
Signal it up to the STM
Correct.
platform. Now, the other thing is, if I start reconfiguring the 10 gigs, does that interrupt it? Does that interrupt my
10
spanning
gigs.
tree or my trill?
So there's no spanning tree, there's no trill.
Right.
One of the nice things about, so actually that's a perfect introduction. Let me hold on that because it brings me to forwarding.
So if you continue that one step farther though, you got to replace that switch because the power supply is dead and it just didn't lose power. What happens there?
So if you're absolutely correct. If you need to replace this switch, obviously you need to unplug this here. You will interrupt communication between us. So you are correct.
Okay, so
There's plenty of other paths to get through that, but you will interrupt
Right, so when you see
active
the
connectivity.
controller architecture, you'll see what are the benefits of SDM that we can leverage here is we can pre-compute failure scenarios. We can pre-compute all the failure scenarios, so we can know that ahead of time. So if there is a cable break, and you'll see this in a second, we already know that we can reroute that traffic in other directions, right? And all that information has already been pushed down to the switch. It says, hey, if this happens, here's a set of backup paths for you to take. And the benefit of having the controller always looking at the topology and seeing, okay, what's going on, is that it can run those calculations constantly and say, okay, I can do this.
Part of my,
Most is never going to get isolated unless there's a break in 2 different places on the rig.
correct.
Yeah.
That was part of my forwarding discussion that I'm trying to get to. Sorry.
From a capacity perspective, you're not just losing connectivity to your neighbors, you're also losing 5 either side pass-through.
Correct.
Right? So we're not just losing 40 gig friendly stuff, we're losing actually 24 channels worth of, albeit recalculatable bandwidth, but that's a massive hit. So I guess that's the downside is you've got a lot of bandwidth floating around, but when you do break the ring, you have an awful lot of bandwidth to remove, potentially.
Yeah, I'm not sure that it's all 240 of everything that goes through, but yes, there is connectivity that needs to be moved.
The key thing to remember here is how often do you, in a large data center, want to go in and grab a device, rip it out, and then replace it again without informing an ops staff?
I think it was Tom who said yesterday, plan for the absolute worst case scenario.
That's
and then
absolutely
you're,
fine.
and then you're
So
golden.
that's where pre-calculating backup paths is true, but for sort of the administrative procedure for removing the physical device. So first off, device fails, you power it off, or you don't power it off, you don't lose those lambdas.
Right.
So that will just go completely through. as soon as you know you have to replace that, it shows that the Plexxi control device has a failure. The intent is for an administrative procedure to kick in to say, remove this section of the ring out of production. In other words, drain the traffic hitless to other parts of the network. At that point, both of the east and west of the device that failed are essentially not carrying any traffic whatsoever. Remove it out, put it back in, enable it or re-enable it in Plexxi control, recalculate topology, and off you go again. So as
really
long as you have administrative procedures in place.
Okay, so really what it comes down to is you want to make sure that if you ever have to pull something out of the ring, either to replace it or to insert a new switch in the ring, be smart, do it at a time of minimum capacity anyway, so that you're not impacting, as you have to shift that traffic somewhere else and recalculate.
But I think, and once I get to the forward topology, right, we can actually proactively move that traffic away from that switch before you pull it out.
No,
right?
I understand. I'm just but the point is, if you're running anywhere near capacity, that's a big chunk to lose. So
Fair.
I guess perhaps logically,
It's kind of equivalent to losing a line card in the spine, right? Because you have lots of capacity coming to that one line card.
The other logical step to this, and you're probably going to get to it with the software, if you're running totally virtual workloads, you can probably have some sort of integration with your orchestration layer. And if you have to drain that, you can literally drain resources away from the gap back towards a high density aggregate area.
Right.
Is that accurate? Okay.
All right, so let me spend about 10 minutes on forwarding topologies, right? How do we actually forward packets within that? Because otherwise Simon doesn't have enough time to talk about control.
The cool stuff.
So you actually mentioned something really interesting there, and I think it's probably something worth highlighting. You actually, in your sentence, you actually made the assumption that you actually have this control over path of where traffic is going. And that actually allows you to open up very different maintenance possibilities in terms of how you treat the network. That is actually one of the key things that the Plexxi Sphere actually gives you, is very discrete control over traffic path. And it actually enables you to start thinking of maintenance events very differently than you would in a traditional network, which is just focused on connectivity.
This concept, if it plays out, gives us the flexibility at this tier of virtualization that load balancers originally gave us with standard workloads to bleed traffic off of one location to another set, do maintenance, and then bleed back.
Right. So there's one of the things that really excited me about the Plexxi solution when I first started hearing about it is the possibility of having very discrete control over traffic flows and having that be something that you can actually provide action on, whether it's actually provisioning, whether it's bandwidth control, or whether it's maintenance.
I got to talk about forwarding, otherwise we're going to run out of time.
The best part of this solution is when we get to the software. So we have to
I got to keep going.
All the cool stuff is coming.
So, well, Lockset, so we were worried about the capacity of the east-west direction. This year, the number of land is going to increase in subsequent versions of the product significantly.
Who told you that?
I don't know.
Cool, you've been here 3 days and someone told you that?
Day 3 for Derek.
It would just be a guess, like, it needs to be bigger, and it would be coming, right?
What does significantly mean?
2 times.
Like 4 times the number of land is.
Two times.
2 times. 2 times?
Well,
Two times.
I
Sometimes.
Just to play on that, even your guys' idea of whatever your stacked ring architecture is, whatever that device is, that opens up all sorts of crazy ideas for even interconnecting rings. I want to hear about the forwarding plane though, because I want to know how you're dealing with loops and stuff.
Okay. So let me quickly do that, because then Simon can actually explain this thing over here. There's this label of SDN that's sort of been floating around on some of the slides and everything else, right? So without going into the virtues of SDN and everything else, the key part for us is the switches themselves do not determine how they forward traffic. They're being told how they forward traffic. So there's no protocols like spanning tree or Trill or SPB or anything else that runs on the switches themselves where they go and figure out where traffic needs to go. Traffic is, topologies are, we call them topologies, forwarding topologies. They are calculated by a controller. Right? The controller OSP software, Simon will talk about it for 45 minutes. That's a really cool part. So he'll explain how you create affinities, how affinities then translate into calculated topology. So bear with me and make the assumption that there is this controlled thing that calculates how to forward traffic. What are the best topologies to move traffic between places on the ring? the controller tells the switches how traffic should be moved. And it's different than OpenFlow, without going into the merits of OpenFlow or not. Right? In our solution, the switches are being told at an abstract level what are the forwarding topologies. Right? So they're not being told for a specific flow, how do I move this packet right, from this source to this destination. They're being given instructions that says, how do I get to anything that sits behind this switch? Or how do I get to anything that sits behind that switch? How do I send that traffic? Which paths do I follow? Right? I have lots of physical paths that I can take. Which ones do I need? Which ones do I use? How do I load balance between them? The switches are being told that in that kind of abstract kind of mechanism, right? It's a topology. It's how do I get there? And there's a reason why we put these little orange boxes on each one of the switches. The switches are given those topologies, and then they make the traffic forwarding decisions in accordance to those topologies. So if they get traffic, they've been told that if that traffic needs to go to someplace behind this switch here, they've been given a topology that says any traffic that needs to go behind this switch, use these links. They're being told that by the controller. The controller has calculated what is the best mechanism to get from where you are to where you need to go. And in many cases it may be, well, I got 2 direct links, I'm going to load balance across those 2 links. And I'm going to simply take destination MAC address 1 sits on one link, destination MAC address 2 sits on the other link. I'm going to sort of split that load between those 2.
So that sort of sounds like the output of a trill or a fabric path in the or FSPF calculation.
Absolutely. Think about it in those terms. Right? It's not. It's different than an SPF calculation, but it is. Well, you're absolutely correct in that it is the result of a calculation that leads into this is a forwarding topology. I'll give you the results of how to forward with that.
Well, to get to this MAC, I send it to this guy over here.
Correct.
Next hop.
Correct.
Yeah. And basically what our controller is a topology computer, right? It's different from Dijkstra, right? It's actually computing stuff based on the affinity inputs, which is what you'll see later. But its output is a set of topologies that that meet those inputs.
Very important to note here, the controller is not a real-time controller, right? We are not expecting the controller to sit in the decision path for a flow. We're not even expecting the controller to react to failures. Right? All of those are pre-computed and passed to the switch. So the switch truly is, once it's been given those topologies, it is independent in its choices of, based on the topologies, where to send traffic. Thank you for that.
You're welcome.
A little strange.
So what that means is, this switch here will get a set of topologies that says, how do I get to destinations that sit behind each one of these switches? And it's not just going to get those topologies to say, okay, how do I get there now? It's also going to get a set of backup topologies. And the set of backup topologies account for every single possible failure in that path. So any switch that can fail, any link that can fail within that topology has a backup. Right? So it's been given a whole set of backup, hundreds of backup topologies. So whenever a switch fails and whenever a link fails, the switch independently can say, okay, I can't use that forwarding topology anymore because that link is no longer there. I'm going to look for the next one in my ordered list of topologies to use that do not use that link or do not use that switch, and I'll move to that forwarding topology. So they've been given the active topology and a whole slew, and they literally are hundreds of backup topologies that they will walk through whenever they encounter a failure. The goal here is very simple. The controller should never be real time. You should be able to turn the controller off and everything should just run. Right? There is no, while the controller is ultimately in charge of calculating topologies, packet forwarding doesn't go through the controller doesn't even get consulted. Failures, link failures, switch failures, sure, the controller will know about it because someone tells them, but the switches do not need new instructions from the controller to figure out how to deal with that. That's an important thing to understand, right? It is architecturally, very deliberately not a real-time controller. It sits off to the side as an optimizer rather than an active participant in forwarding traffic. So I talked about forwarding, right? So these topologies have been given. So for layer 2, it's obviously very simple. A packet comes in, needs to go to a destination that sits behind here. This switch has been given a bunch of topologies that says, how do I get to everyone that's behind this switch. By the way, we know that A is behind the switch because all these switches communicate. So MAC addresses are exchanged between all the switches. So every switch has a view of where all the MAC addresses are.
Is that by flooding, I assume?
No, there's a control protocol that we exchange that way. So we don't flood them, so they don't learn in the traditional bridge way. We only learn on an access port here, and then there is an active communication between all the switches to exchange MAC
So
address
it's between
attachments.
the switches and not from the switch to the controller to the switch?
Correct. It is between the switches and then also to the controller. So the controller will have it, but the controller is not in the path of that distribution. Right? So a packet comes in.
So what, so what if it's not cached? It's got to learn somehow.
It's flooded.
Right.
So
Okay.
if we don't know about it, we'll flood it.
Flooding is localized to the switch, or is it flooded to the broadcast?
It's actually flooded throughout the ring.
Okay.
Just like a regular switch network would do. If we don't know where a MAC address is, we'll flood it until one of the switches has learned it. The moment one of the switches has learned it, he'll pass it to everybody else, and everybody else will know where that MAC address is. So in this case, packet comes in here, destination is A behind there. We know what's behind switch number A. We figure out which topology are we supposed to use to get to this switch over here. We'll stick the packet on one of the links within the topology based on some load balancing metric that we've been provided. That's basically layer 2 forwarding. Right, so yes, we flood to go and find out where MAC addresses are. Once it's learned,
one switch learns it.
One switch learns it, passes around, every switch will know where every MAC address is. Doesn't mean it gets installed into hardware, right? Because obviously hardware has limitations on how many MAC addresses you can support. It is exchanged. That little orange box, the controller, the control plane there, knows where that MAC address is. We'll only install it in hardware if it's needed. Or if it's an active communication through that switch, we'll be actually install it in the hardware.
So if I have 200,000 MAC addresses that would blow out a CAN table, you're pushing those into a hash upstream onto.
I will only push those into hardware, the ones that I'm actively using on that switch.
Now does that go north to the controller?
So we also send a copy to the controller. The controller knows where all the MAC addresses are.
But that's the computing to topologies layer we're trying. Okay.
So then when
very soon, Martin's going to
really soon, Simon will tell you how the controller actually uses it.
It's actually very important because then it really brings this together when you see how. If you're forced to telnet to each of these switches and configure them manually, you don't have much of a solution, right? So it has to work from an overall control perspective.
But you understand why we're digging into this side of it, because this is the failure side we understand.
Yep. Right.
And then understanding the software layer, you're right, Rob.
But I think we'll get onto the software, and Martin can stay there and answer stuff, and I think it'll solidify everything we're saying when we go into the software.
Value in Plexxi is in the software, not the hard forwarding.
Absolutely.
Yeah. Yes.
You can pretty much assume that the product is a forwarding plane that's better than your Ethernet, otherwise you're not going to buy it.
Right.
Right? So the value's in the software. That's what I really want to see is the software.
And so, and let me get there real quick. I'll be the first to say, right, the switch for us, right, in the forwarding is simply a tool, right? It is simply it's cool because it's got some cool technology.
I'm just putting my laptop here.
But it's really nothing more than a tool to enable, right, the very controlled
If you couldn't emulate Trill at the very least, we'd have a problem. Right? So your features are going to have to be at least that or greater.
Right.
So the assurance that I would go away with is that the forwarding path, there's an answer for all of these objections that we're going to have because they'll have thought it out. Because if they're not better or smarter than what the existing vendors are, they're not going to be in business. Right?
So one other benefits of kind of starting from scratch, using custom off-the-shelf silicon was that we could choose what kind of CPU to add to that individual box. So aside from being able to
C2 is the local controller, right?
Correct. On the box itself, we have multiple Intel cores running. We have infinite capability to extend software there. So you could almost argue that on its own, it's already cool to have our switches because we've got 5x, if not more, capacity than most others that run, as top fractions there. So we haven't skimped on any of those.
No.
So let me make 2 more points, and then Simon can talk about the real cool stuff. So I talked about generic forwarding, right? How do I get to a destination that's behind a switch somewhere? What I haven't talked about is specifically if I have very definitively created an affinity between 2 endpoints, right? So I have an application here and an application there, and I've asked, or I've told the controller that application requires their traffic to be isolated from everybody else, right? That that is very specifically told to the switches, right? The switches are being told very specifically about that communication. And it's being matched by the switch, put on a specific link, right? Let's assume it's this one. And that switch has also been instructed, nothing else can go on that link. So that link may be not part of any other forwarding topology, because we've asked specifically only that communication will go on that link. Everything else is pushed off to the side, right? And that's where the controller comes in, right? It actually starts making those decisions between, well, if you've asked me for high bandwidth communication between these two, or isolated communication between those two, I need to take all the other topologies and move traffic out of the way. So I may need to go, for other traffic, I may need to go this way, because you've specifically said this direct connectivity, I want it dedicated between A and B. Those are the types of things that Simon will talk about what the controller can do. Last point I want to make, IP forwarding, because you asked. I talked about this as sort of basic layer 2 forwarding, right? Layer 3 forwarding, again, slightly different paradigm here. Every switch will be the default gateway for every single VLAN, right? So when a packet comes in here for, on VLAN 10, needs to go to something here on VLAN 100, this switch here will route it. Within our fabric, or within our connectivity, all VLANs exist, right? So VLAN 100 actually exists at the back end of this one here. He will route that packet. Layer 2, follow this topology, find its way over here, and out. On the way back, traffic on the way back will be routed here. Right, so we route on the ingress switch. The first switch you hit is the one that will route. All switches share the same default gateway address for a specific VLAN. They all share the same MAC address for a specific VLAN. Right, so no matter where you are, right, a VLAN can exist anywhere on that ring. The default gateway is going to be the same. IP address is going to be the same. MAC address is going to be the same. And it's not because we've designated one of these switches to be the router for that VLAN. No, it's because every switch is a router for that VLAN. That makes sense? Right, so this means that routed traffic doesn't need to go to a specific switch. First switch that sees it will route it.
Cool.
For every single VLAN.
Yes.
It's the software I want to see. I don't really care about switching.
Wow.
Thank you for that.
I mean, I believe you. I mean, it's all explained. I mean, to me, it's,
So